Hey friends, so welcome to Unit 2. Welcome to Unit 2. So in Unit 2, we're going to tackle nonlinear systems of equations and inequalities, okay? And this first few lessons, what we're going to deal with is trying to solve systems where one or more of the equations is not a straight line, okay? So this is going to feel, I'm hoping, the first couple of lessons will feel familiar to 10C, okay? Because in 10C, we did a whole unit on solving systems, okay? We solved by graphing, we solved by substitution, and we solved by elimination, okay? If you don't remember those words, or if you think you might need a little bit of a refresher, I want to encourage you to go check out the 10C videos. They're all done and on YouTube waiting for you. So check those out first, maybe just as a little refresher to help you just get the brain juices flowing again. Okay. If it's been a little while since you've done some math. Okay. So today we're going to tackle solving systems of nonlinear equations, and we're going to do it by graphing. Okay, so there'll be a review of graphing by hand. There'll be a review of graphing by graphing calculator. I'll try and give you bits and pieces of everything. Okay. Okay. Awesome. Let's get going. So, recall. A system of linear equations is two or more functions that work together to help us find the solution or solutions when we have more than one equation. So an example I've given you here is x plus 6y equals 10 and 3x minus 2y equals 1, okay? Both of those are straight lines. I know they're straight lines because we have an x, we have a y, and we don't have any exponents on anything, okay? To solve a linear system means to determine all the ordered pairs that satisfy both equations. Now, just as a little reminder, this word satisfy in math, what that means is it works, okay? So we could say that the point 4, 1 satisfies this equation right here, okay? Because if I plug in 4 for x and 1 for y, I get 4 plus 6 equals 10. That point works in that equation. Now, does it satisfy this equation? Well, if I plug in 4 for x, I get 12. 1 for y, I'll get 12 minus 2. That does not equal 1. Okay, so while the point 4, 1 satisfies the top equation, it does not satisfy the bottom equation. Therefore, it is not a solution to the system. Okay, in order to be a solution to the system, it must satisfy both equations at the same time. Okay, so graphically, back to our note here, graphically, this means that the solution to the system is the intersection of the two lines. Okay, so we're looking for that point that is common to both lines, and that's called the point of intersection. Okay, all right. So there are three possibilities for the solution of a system of linear functions. Now, we can have one solution, no solutions, and infinite solutions. I want to give you a picture of each one of these, and then I want to talk about how we would know whether it's one solution, no solutions, or infinite solutions based on looking at their slopes and their y-intercepts. Okay, so here's what one solution might look like. It's essentially just two different lines that intersect at one point. Okay, in order to have two different lines that intersect at one point, you need to have their slopes different. Okay, and I'll write that down in 1 second. To have no solutions, they would need to be parallel. And then to have infinite solutions, they're right on top of each other. Okay, so you can see that the blue line is directly on top of the orange line. Remember, we said that a solution is every point that satisfies the equation, okay? Both equations at the same time. Here, there's one point right there that satisfies both equations. Here, there's no points that satisfy the equations. And here, sorry, there's no points that satisfy both equations, okay? There's lots of points that satisfy the purple equation here, and there's lots of points that satisfy the blue equation, but there's no point that satisfies both at the same time, okay? Whereas in the infinite solution, every point on that line, because they're overlapping each other, every point on that line is a point that works in both equations at the same time. Okay, so I promised you we were going to compare the slopes and the y-intercept, so I have that below here. If I have one solution, essentially the slopes are different, okay? It doesn't matter about the y-intercepts. They could be the same, they could be different, but the slopes are different if I have one solution. If I have no solutions, the slopes were the same, but the y-intercepts were different. That's what made a parallel line, okay? And then if I have infinite solutions, the slopes are the same, but the y-intercepts are also the same. That's what makes it be the same line, okay? Okay, so everything I've done so far, this is kind of a quick review of 10C, okay? If, say, the last 45 seconds of this video has completely blown your mind and stressed you out, I want you to stop, go back and look at the 10C videos. There's one on graphing, there's one on substitution, there's one on elimination. And just go through those a little slower so that you have time to just figure things out and make sure you're ready for today, okay? It's totally okay if you forget stuff, but we just need to make sure you do what you need to do to jog your memory, okay? All right, so I just said this, but there are three methods to determine the solution to a system. We can do it by graphing, by substitution, or by elimination. Today, we're just going to focus on graphing. And like I said earlier, we will focus on graphing by hand and graphing by calculator. Tomorrow, in the next lesson, we will get into substitution and elimination. Okay. All right, so solve the following system of equations graphically. So we've got y equals 2x minus 3. We've got x plus 3y minus 33 equals 0. First of all, I want you to say that both of these are linear because they have an x, they have a y, and they don't have any exponents. The red one, the y equals 2x minus 3, I'm ready to graph that. It's in a nice form for me, but the purple one's not. So I want to do some rearranging to the purple one. I'm going to have to subtract x from both sides, and I'm going to have to add 33 to both sides. That would give me 3y equals negative x plus 33. Now that doesn't have y by itself yet. I'm trying to put this into y equals mx plus b form. That's called slope y-intercept form because that's easier to graph, right? I'll know exactly where my slope or where my y-intercept is, sorry. And I'll know from that y-intercept how to apply the slope, okay? So I have to divide everything by 3, okay? And that's going to give me, the red graph hasn't changed, 2x minus 3, but the purple graph can now be written as y equals negative 1/3 x plus 11. Okay, so again, I subtracted x from both sides, I added 33 to both sides, and then I divided everything by 3. Okay? All right, so now I'm going to go ahead and graph these guys. The red guy, I know I have a y-intercept at negative 3 down here. And then I know I go up 2 over 1, that's what my slope says. Up 2 over 1, up 2 over 1. So I'm going to plot some points there, okay? Then for the purple guy, I know I start at 11, way up here. And I'm going to go down 1, right 3, down 1, right 3. And I'm going to plot some points. I'm going to get out a ruler so I can connect those dots. I always want to use a ruler here so that I ensure my lines are straight. Otherwise, it's going to throw off my answer, right? So when I have a ruler and I connect those dots, I see that there's one intersection point, and the intersection point is right here at 6, 9. Okay, 6, 9. Now, the next thing I want to do is I want to walk you through this exact same question using a graphing calculator. So just a quick review of your graphing calculator. I am going to switch my screen in 1 second to the Casio. But if you have a TI, you can follow along. I'll help you through the TI steps as well, okay? Okay, so the first thing we would have to do is the exact same as the first thing here, which is make sure both of them are y equals, because your graphing calculator wants it as y equals when you go into the spot where you can put all your equations, okay? So just remember, we've got 2x minus 3 I'm actually going to write that on a piece of paper here so that I'll remember when I switch screens, and negative 1/3 x plus 11. Okay, negative 1/3 x plus 11. So give me 1 sec to switch screens here. And we're going to go to a graphing calculator. Okay, so now when I go to my graphing calculator, as a Casio, I want to go menu and then press the graph feature. If I'm a TI, I want to press the Y equals button, which is right up here on a TI. Okay, so I'm going to input these into Y1 and Y2. So Y1 is going to say 2x minus 3. And then Y2, just hit execute to go down to Y2. Negative 1/3. Okay, x plus 11. Okay. Now, just a reminder, I know we've talked about graphing calculators before, so I'm hoping that this is okay, but your variable button, the X is your variable button, which is right here on a Casio underneath your alpha sign. If you're a TI, it's actually, I think it's right beside your alpha sign. It'll be right over here and it says X theta TN. Okay, that's the button to get your variable there. Okay, and the only other thing I'd want to say at this point, I'll just do it in Y3 so you can see it. If you're an older model Casio or an older model TI that doesn't have that fraction button availability, what you want to do is you'd want to go bracket, -1 divide by 3, close your bracket, and then put X. Okay, so every fraction that you write, you just put as a division statement inside its own set of brackets. Okay. Okay, I'm just gonna shut that guy off because I don't actually want to graph him. The other thing before we look at a picture here that I wanted to mention is it's often a good idea to somehow distinguish if you have a black and white calculator, like it's not color, that's what black and white means. It's often good to distinguish between your Y1 and Y2. So I just want to show you how to do that. On a Casio, what you would do is you'd go to Tool, which is F4, and then choose Style. Okay, so like you see F1 is your thin line, which is what kind of the default is. So you could change one of them to a thick line by pressing F2, and then you could compare on your graph a thick line versus a thin line. Okay. On a TI, you can actually do the same thing, but what you'd want to do is you want to have your cursor on Y1 or Y2, whatever one you want to do, and just left press until you're over to the other side of Y1. And what you'll notice is once you get over to the other side of Y1, it'll start flashing at you. And if you hit enter, it'll change that from a thin line to a thick line. Okay, just when you're looking at a black and white calculator, it's just a little easier to distinguish. Okay, not a big deal if you don't, just trying to help. Okay, so now what we want to do is we want to graph that and take a look at the picture. Okay, so my window is a little off because of whatever last thing I did on my calculator was. So I'm going to go to a standard window. I do that by pressing F3 to get into window and then F3 to say standard. Okay, on a TI, that's zoom 6. Okay, so now you all should be looking at this picture. But again, that's actually not the greatest picture right now because I don't see all the important points. I like to see the y-intercepts. I'd love to see the x-intercepts if possible as well, which means when I look at this, I would like to bring my y max up and my x max up a bit. Okay, so I'm going to go back to window. I'm going to bring my x max, to maybe 15. I'll probably go by 2s now instead. And let's do y, oh, sorry, I did that backwards, hey? Oh, no, that's okay. Let's do my y max also to 15 and 2. And let's just see what that picture is. When I was changing those original numbers, I was thinking about y. Okay, so I see my y-intercept, which is great. And I see the point of intersection, which is great. But just for fun, I would really like to see that x intercept as well. So I need to bring my x max up just a wee bit more. So I'm going to go back to my window. And TI kids, you do the same thing. You just press your window button. Okay, I'm going to change that to maybe 25 to see what that does. Okay. Oh, I still don't see it. Okay, that's okay. I almost see it, but let's go to 40. Don't want to waste your time here on the video. Yeah, okay. So now I see all my important points. I see the x-intercept, the y-intercept, and I see the actual intersection of the line. Now, to graphically get the intersection of the line on a Casio, I would just press G-solve and then intersect. So it's F5, F5, and then I see it's 6, 9. Okay, just like I did by hand. On a TI, you would go second trace, option 5, and then you'd press enter 3 times. Okay. All right, so I'm going to go back to the PowerPoint. Okay, and we see the same thing that we did on our graphing calculator. I'm just going to show you the picture I have here of the graphing calculator. Okay, I didn't change my windows on this to go all the way to the x-intercept. I just needed to see the intersection point, so I left it there. When you're drawing things, if you were to hand draw things, it's nice to see both the y and x intercepts. Okay. Okay, and then I'm going to conclude the solution is bracket 6, 9. A reminder, the solution is the coordinate points, and coordinate points are always written as bracket x, y, close bracket. Okay. Okay, so now, again, that's really been a review of solving systems by graphing with linear systems. Where we want to take you today is we don't want both of them to be a straight line. We want to throw in a parabola, or maybe we want to throw in 2 parabolas. That'd be fun. Okay, so now we will begin solving systems that include nonlinear functions. But the idea is the exact same. Okay, we're going to determine the point or points of intersection. These systems can have 1 linear and 1 quadratic, or 2 quadratic. Okay, so here's the first one we're going to do. We're going to solve the following system graphically, and I'm going to again walk you through by hand. They're both y equals already, so that's kind of nice. I'm going to go to the pink one first because we know exactly how to draw that one, right? We are going to go to our y-intercept at 1. And then from there, we're going to go up 2 over 1, up 2 over 1. We're going to generate some points, and then we're going to take a ruler and draw a straight line. The green guy is a parabola. It's a quadratic, right? And we know that it's either going to look like this or it's going to look like this. Okay. It's going to be curved. It's not going to be a V. It's going to be a nice curve. Okay. I would hope that you can look at that and be confident to say it opens up, because my A value is positive. Okay, we've already dealt with that. So really the easiest thing to do is let's just plug in some numbers. If I plug in -2, -2 squared is 4, 4 minus 2 is 2. So I know I have the point -2, 2. If I plug in -1, -1 squared is 1, and 1 minus 2 is -1. So I know I have the point -1, -1. I can put that guy right there. Plug in 0, I get out -2. Plug in 1, I get out 1. Plug in 2, I get out 2 again. Okay, so this is me plotting all those points. I even went to -3. -3 squared is 9. 9 minus 2 is 7. So that's where my 7s come from for -3 and for 3. Okay, so now I'm going to have a nice curve for those green dots, and I'm going to have a nice straight line for the pink dots. And I get something like this. And I can say, hey, I actually have 2 solutions to this. There are 2 intersection points, which means there are 2 values for x and y that would work in both of these equations at the same time. Okay, one of them's at -1, -1, and the other is at 3, 7. Okay, so 2 solutions, -1, -1, and 3, 7. Okay, now I want to walk you through doing this one on your graphing calculator as well. Same sort of thing. I just need to switch screens. Okay, so I'm going to just exit to get back to my y equals. Okay, the first guy was x squared minus 2. So x squared minus 2, and I hit execute. And then the second guy was 2x plus 1. So 2x plus 1, I hit execute and I draw. Okay, I am going to change my window setting now. I don't need all this dead space over here, right? So let's put my x, x's to -5 and 5. And let's put my y's, maybe we'll go -4 to 10. Okay, just see what that's like. So I'm going to go to window. I said -5 to 5. I'm going to do a scale of 1 there. And then I said -4 to 10. We'll just see what that's like. Okay, so then I exit and draw. In TI Kids, you do the exact same thing. You just press window and you do the exact same thing that I just did. Okay, so I see these nicely. On a Casio, I'm going to press F5, F5. It's going to take me to the one on the left, which is that -1, -1. Okay, then if you right-click over your right button here, it'll just take you to the very next one, and that's 3,7. Okay, on a TI, you do that second trace 5, but then what you're going to have to do is move your cursor over close to the one you want, and then press enter, 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 and it'll give you that one. It doesn't have to be right on it. It just has to be close. And then for the second guy, you just have to go through the process again. So you go second trace 5, move your cursor to the other one, and hit enter, enter, enter. Okay. All right, so back to the PowerPoint. I had a picture that looks like that, and we got the same answers. Okay. All right, so now we're going to do this guy graphically. The thing I want you to notice with this guy, and I'm not going to do this one by hand anymore, but I would encourage you to keep trying by hand. I'm also not going to go back to, I figure 2 is enough in the video. I'm not going to go back to the graphing calculator anymore. I have pictures already set up to show you what you should get, but I won't walk you through that anymore. What I do want to walk you through here is making sure you can rearrange it to y equals, okay? Because if you don't have the right equation, that kind of sucks, right? Everything else is gonna fall apart. So what I'm gonna do here is I'm gonna take this -y and I'm gonna move it over there. Then it'd be +y. So I'd have y equals x plus 1, okay? The other guy, I'm gonna leave that y where he is because he's already positive. I'm gonna bring everybody else over to the right. So that's gonna be y equals -x² plus 6x and -3. Whenever you cross the equal sign, you essentially switch signs, right? Okay, so that leaves me with this. I've got that x plus 1, and I've got -x² plus 6x minus 3. Okay, I want you should shut me up, pause me for a second, try and graph this, try and get the intersection points before I show you the picture. And I'm going to show you the picture now. This is what you should have got. And we would have gotten solutions of 1, 2, and 4, 5. Okay, 1, 2, and 4, 5. Hopefully that went okay. If not, rewind, try again. We got all the time in the world together, okay? We could do this all through the night. You just have to keep rewinding and going again, okay? That's what I'm here for. Okay, so there are 3 possibilities for the solution or solutions when we have a linear with a quadratic, okay? Either we have one solution. If we have one solution, it might look something like that. 2 solutions, okay? Or no solutions, where there'd be no points that are common between the 2 functions, okay? One solution, the graphs intersect at one point, and that point is called a point of tangency. For 2 solutions, the graphs intersect at 2 points, and that's called secant. And then for no solutions, the graphs just don't intersect. Okay. All right. So just to recap what we've done so far, I've reviewed with you linear with linear. And now this last example has been with linear and quadratic. So if you think about what we haven't tackled yet, that would be quadratic with quadratic. Okay, so that's going to be the next thing we do. So solve the following systems of equations graphically. This first top one is all set up for us. It already says y equals, so I can go put that into y1 right away. The guy below, though, we need to do a little bit of work on him. I'm going to take the negative y, bring him over there. So then that'll be positive y. Then I'll have to take the negative 19 and bring him over. It's essentially, algebraically, I'm adding 19 to both sides, right? Okay, so that's going to give me y equals x squared plus 8x plus 19. Sorry, I don't have my mouse on. Okay, so I didn't change the first guy. The second guy, I rearranged so that it's y equals. I'm going to go put that into my graphing calculator for y1 and y2. You go ahead and do that. And then this is the picture that you should have gotten. And we should have points of intersection, 2 points. The solutions are -5, 4. That was the one on the left. And then 3, 4 is the one on the right. Okay. This is going good, right? We got this. We got this. Okay. So a system of quadratic equations involved 2 quadratic equations, and both of the graphs will be parabolas. So there are actually 4 different things that could happen here. And I'm just going to go through each one. We could have one solution. So I've shown you just 2 different examples where you could have one solution. Okay. We could have 2 solutions, and I've shown you a couple of examples of that. So both of these intersect each other twice. We could have no solution. So a couple of examples of that. And then because it's a quadratic with a quadratic, we could have infinite solutions as well, if those quadratics were directly overlapping, if they were right on top of each other. Okay. All right, awesome. Let's end our time together with a word problem, because I couldn't think of a better way to end our time together. I know how much everybody out there loves word problems. Okay, a pelican flying in the air drops a crab from a height of 30 feet above the water. The distance the crab is from the water as it falls can be represented by the function h of t equals -16t squared plus 30, where t is the time in seconds. Now, I'm going to stop right there. Half of you just shut down because I've read too many words at this point, and you're like, oh, this is too hard. Okay, this is not complicated. We can't shut down with word problems just because there's words there. Okay, that's something that we all kind of have to push through and say, no, I'm going to figure out what I'm told. I'm going to figure out why I've been told it. And then I can figure out how to get to a solution. Okay. What have I been told? Why have I been told it? And how does that lead me to a solution? So just to recap, a pelican has dropped a crab. So the crab is now free falling down into the ground or the water. Okay. Now, to catch the crab as it falls, a gull flies along a path represented by another function, g of t equals -8t plus 15. Graphically illustrate if the gull will catch the crab before the crab hits the water. So I've got the crab falling, I've got the gull diving for it. Will the gull and the crab intersect in time? Or will the crab fall either to his death or, oh no, it's above the water. It won't be his death. He'll fall into the water and then he'd be safe if the gull doesn't get him. If the gull does get him, this crab is having a very, very bad day. He was caught by a pelican and then grabbed by a gull. But let's see. What we want to do is we want to graph h of t and graph g of t. So put one of them in y1, one of them in y2, and then I do want you to pause me for a second, do that, and I want you to play around with your window settings so that you can compare my window settings, okay? So go ahead and pause me. Welcome back. Okay, so here's a picture that you should have gotten, okay? Now, if you're trying to compare my window settings, my y values go from -5 up to 35. And then my x values are going from like -0.5 to 3, okay? So here is the flight of the crab as it drops, and here is the flight of the gull as it goes for the crab. And we can see, yes, the gull will intersect the crab right here. The crab does, in fact, have a very, very bad day. When does that happen? Well, we just find the intersection point. So on a Casio, we're going to go F5, F5. On a TI, we're going to go second trace 5, enter, enter, enter. And we should get that the gull will catch the crab 1.25 seconds after it was released from the pelican, okay? 1.25 seconds after it was released. It was released from the pelican right at time 0, okay? Awesome. You guys got this. All right, that's where I'm going to leave you for today. I've posted your homework. You can get started on that. Make sure you're trying to visualize what's happening and make sure you're being nice and neat and make sure you're asking me questions when you don't understand. Okay, that's what I'm here for. All right, I will see you guys next time when we start doing the exact same thing, but we're going to take a more algebraic approach with substitution and elimination. Okay, so I'll see you there. Take care, guys.